To understand the first fundamental theorem of calculus at a rigorous level, we have to move past intuition and use the formal tools of real analysis. We start with a continuous function curve, defining an area accumulating underneath it up to a specific moving point, x. To measure how fast this area is growing, we isolate a microscopic sliver added over a tiny forward step. We write out its exact rate of change as the amount of new area divided by that step's width. Because the curve's height fluctuates across this tiny step, the added area isn't a perfect flat-topped rectangle. This makes it impossible to calculate a single exact height by simple division. But because the function is perfectly continuous, the extreme value theorem guarantees it must hit a specific highest and lowest point. These points define a strict maximum and minimum bounding box for the area. We translate this visual box into an algebraic inequality, physically trapping our rate of change fraction tightly between the minimum and maximum height values of the curve. Now, we invoke the squeeze theorem by shrinking that forward step down to absolutely nothing. The maximum and minimum points slide along the continuous curve until they physically crash into the exact same point. Because our fraction is forever trapped between these two colliding bounds, it's forced to equal the function's height at that exact spot. This rigorously proves that the derivative of the area is simply the function itself. So what happens to that total accumulating area we started with? Its exact mathematical rate of growth perfectly matches the curve's height at every single point.